Start. Okay, I'm really happy to introduce our next speaker, Andrea Svob. It is not the first time for her to give a talk on this workshop, and I'm really happy that she continues to be with us. So the floor is yours.
Just a second. Okay, so thank you very much, Elena, for the nice introduction, and thank you once again for inviting me to participate to this very nice conference. I'm really privileged to be here and to be part of this conference. So today I will talk about codes from orbit matrices of seidal and Laplacian matrices of strongly regular graphs. So I will try to explain you the research that I was doing with my colleagues, Dejan Cenkovic and Ronan Egan. So while we were doing, they were both also from my department of mathematics, but now Ronan is in Dublin University, and Dejan is my colleague from Department of Mathematics. So in this talk, I will try to explain you the research that we were doing and we published in this paper. And this is actually combining some methods from the graph theory and applying to the coding theory. So in order to explain you what we have done, I have divided my talk into a few parts. First of all, I will give you some introduction details about this topic. Then I will give you some motivation part, and then I will try to show you what is the method that we use to combine these two theories. Okay, so first of all, we will need some basic facts about graphs, especially strongly regular graphs. So today, strongly regular graphs were seen before, and also you have seen this picture, but I will again repeat it. So we say that a graph is regular if all the vertices have the same degree. You can see in this picture, this graph is Peterson graph, and it is regular with degree 3. We say that a regular graph is strongly regular of type or with parameters v, k, lambda, mi, and we will denote it by SFG v, k, lambda, mu, sorry. If it has v vertices, if it is of degree k, if any two adjacent vertices have lambda common vertices, while any two non-adjacent vertices have are both adjacent to mu common vertices. We can see that very easily in this picture. So this is a regular graph. As we said, it has 10 vertices. Every two adjacent vertices, you can take any, but for example, these two are adjacent. They have no common adjacent vertices, while any two non-adjacent vertices, for example, these two have exactly, in this case, one common vertex. So this is a strongly regular graph with parameters 10, 3, 0, and 1. Very known fact, which is very easily to see, is that if you have a strongly regular graph, then the complement of a strongly regular graph will be again a strongly regular graph, and we can calculate its parameters. So if the parameters of a strongly regular graphs are vk lambda mu, then the parameters of its complements are these ones. Okay, so you can always be sure that when you have a strongly regular, its complement is again strongly regular. Good. So to any graph, not just strongly regular, you can associate adjacency matrix, which will actually describe you the adjacency between vertices of this graph. So we can denote G to be a graph having the adjacency matrix A, and we will label the rows and columns of this matrix by V1 up to V up to the number of the vertices that we have in this graph. Okay, so to this graph, I'm emphasizing not just to strongly regular, we can associate few more matrices, not just adjacency matrix. One of these metrics is seidal adjacency matrix. The seidal adjacency matrix of a graph G is the matrix that is defined with this formula. Actually, it is a matrix that has three entries. It can be 0, -1, and 1. It is 0 when we have a position of the same vertex. It will be -1 when two vertices are adjacent, and it will be 1 if two vertices are not adjacent. Okay, so actually the seidal matrix can be also defined in this way. So if you take all ones matrix, identity matrix, and adjacency matrix of a graph, and if you put this in this formula, you will have the seidal matrix of a graph. The seidal adjacency matrix is used for switching, for seidal and some other type of switching, and it is very commonly used in algebraic graph theory. In this work, we were using seidal matrix in a way that we try to use this matrix in order to obtain codes with nice properties. Okay, this is the seidal matrix is one type of the matrix that we will use in this work. The other matrices that we will use are Laplacian matrices. Okay, so Laplacian matrices are defined for a simple graph. So let G be a simple graph. So it is a graph without loops, having adjacency matrix A. Okay, so if you take D to be the diagonal matrix with the degrees of this graph on the diagonal, where the ordering is the same as ordering in adjacency matrix, then if you take, if you extract from the adjacency matrix, you will have the Laplacian matrix of this graph. Usually matrix is displaced and it is called Laplacian or admittance matrix. Okay, so very similar as Laplacian matrix, it is defined signless Laplacian matrix to be the matrix with absolute L, which is adjacency matrix plus diagonal matrix, which has degrees of this graph on the diagonal. Okay, so these three matrices were base for our research in order to see how they can be used to obtain codes with nice properties. Okay, I will show you what kind of properties they have and how we use them in application. Okay, so I will just quickly go through the main facts about codes. So code of length n over the alphabet is the subset of q to the n. Elements are called code words. In this work, we are interested in qary linear codes. So it means that our alphabet will be fq, and the code is defined to be an m if it is of of dimension m to be an m-dimensional subspace of the vector space fq to the n. Okay, so if you take x and y to be two code words or two elements from fq to the n, you can define the Hamming distance between these two words, which is the number which is labeled by d, and it actually says on how many positions these two code words differ. The minimum between all the Hamming distances between every two code words from the code C is defined to be the minimum distance of the code C. So if you have a query linear code which is of length n, dimension k, and distance d, then we will denote it with nkdq code, and I will call it nkdq code. To any code, you can associate its dual code, which is the orthogonal complement under the standard inner product. So it means that in this dual code lies all the vectors which inner product with all the code words from the code C is equal to 0. And we say that the code is self-orthogonal if it is contained in its dual code, and it is self-dual if equality is attained or if it is equal to their dual. Okay, so we will be interested here in self-orthogonal codes. So I will not point out all those codes that are not self-orthogonal, because our method works for obtaining self-orthogonal codes. The self-orthogonal codes are one of the nice family of the codes that you can obtain because of its easy way of decoding, of its nice properties, and some of the best codes, some of the nicest codes that are found are self-orthogonal or even self-dual. Okay, but as I said, we were interested in combining or actually answering on the question how we can use matrices that are associated to strongly regular graphs in order to obtain nice self-orthogonal codes. What was the motivation for our work? So if you go in the literature, you can see that codes that are spanned by adjacency matrices of strongly regular graphs were investigated before. You can find these two very nice papers in which the authors were interested in codes that were spanned by adjacency matrices of strongly regular graphs. In 1997, Tonchev, in his paper, was investigating binary codes that are deriving from Hoffman-Singleton and Higmans-Sims graphs, while Hammers, Peters, and Riekewersel, in this work in 1999, were interested in binary codes of some strongly regular graphs. Okay, but they were using just normal adjacency matrices of strongly regular graphs. Okay. Block designs as incident structures that Dejan defined in the talk before me. So block design, just to remind you, is an incident structures with parameters 2 vk lambda, which says that you have with points, you have the blocks that are all of the same size, if you are speaking about parameter key then key, and have the property that each 2 points are together in lambda blocks. Okay, so incidence matrix is actually a matrix that is speaking about incidence between points and blocks. And incidence matrices of block designs were studied codes obtained from incidence matrices of block designs, which were studied in many other papers, in more papers than adjacency matrices of strongly regular graphs. And you can find them for example, in the book Designs and Their Codes. It is very, very nicely written about codes that are spanned by incidence matrices. Some of the nice results that I'm emphasizing here are those obtained by Boyukliev, Fak, Wiene, in which they were interested in two designs or block designs with these parameters, and codes obtained from these designs and their related Adamar matrices. In this paper, Tonchev studied quantum codes from finite geometry and combinatorial designs. And in this paper, you can also find very nicely described studies about codes spanned by incidence matrices of block designs. More about combining and obtaining codes from matrices that are related with designs and graphs are those that are related with orbit matrices of designs and graphs. This research, we can say, actually started with a paper by Harada and Tonchev, in which they gave a method for constructing self-orthogonal codes from orbit matrices of symmetric designs, but with fixed point-free automorphisms. So here they obtained a very nice family of codes from particular designs having fixed point-free automorphisms. This research was generalized in these later works in order to the authors obtained self-orthogonal codes from orbit matrices of two designs with no restrictions on the automorphisms. And moreover, this research was extended on orbit matrices of strongly regular graphs. And in the last, actually, we generalized this work to obtain self-orthogonal codes from equitable partitions of association schemes. Okay, so the main idea that we are now approaching to the fact that was crucial for our studies are two papers that I will now mention. In this work, we actually generalized the notion of orbit matrices of incidence matrices on orbit matrices of Adamar matrices. And we saw that this has these orbit matrices have had very nice properties in a way to obtain nice family of codes. Why one should try to, why did we try to introduce the notion of orbit matrices in this case of Adamar matrices? Because orbit matrices are always defined with respect to some automorphism groups. In this work, we introduced the notion of orbit matrices of Adamar matrices with respect to their permutation automorphism group. And we show that under some conditions, these orbit matrices yield self-orthogonal codes. But moreover, this notion of orbit matrices actually gives us a wider range of automorphism groups. And if you have a wider range of groups, then it means that you can have potentially more orbit matrices. So this was the main motivation and the main idea why one could try to introduce the notion of orbit matrices of Hadamard matrices, which we know are not 0-1 matrices. We extended this work not just to Hadamard matrices, but also to Weill matrices. And we show how one can construct self-orthogonal and Hermitian self-orthogonal codes from orbit matrices of Weill matrices having the entries in a finite field. In this case, the fields of 2, 3, and 4. Okay, and this actually leads us to the main idea, which was for us, let us try to introduce the notion of orbit matrices of certain integer matrices, such as seidal and Laplacian matrices of strongly regular graphs, and let us try to show that for suitable graph parameters, one can construct codes with nice properties, or one can obtain self-orthogonal codes over finite fields. Moreover, we saw that these techniques is working also for obtaining self-orthogonal codes of not just over finite fields, but also over rings of integers. Okay, so what did we need to define, and what we need to show before trying to obtain codes? First of all, we needed to see what kind of properties seidal and Laplacian matrices could have in order to introduce orbit matrices of this type of matrices. So let M be an n times n matrix. A permutation automorphism of the matrix M is a pair of n times n permutation matrices P and Q, such that this expression holds. The set of all such pairs forms the permutation automorphism group, which we will denote with P out of M, and we will call it permutation automorphism group. It is well known that an automorphism of a graph G is a permutation of a vertex set V that preserves the edge set. And it is well known that an automorphism out of G induces a permutation automorphism of the adjacency matrix of a graph, and it is of the form PG. So actually, it follows that any automorphism of a strongly regular graph G induces a permutation automorphism of its seidal, Laplacian, and signless Laplacian matrices. And this was one of the very important facts that we needed in order to go moreover, or in order to define an orbit matrix of an integer matrix. Okay, so how you can do that? Let G be a permutation automorphism group of an integer matrix M. So you are starting from an integer matrix. So I'm emphasizing here that it does not have to be 0-1 matrix. It can be an integer matrix. And let G be a permutation automorphism group that is acting in T orbits on the set of rows and the set of columns of the matrix. We can denote the G orbits on rows and columns of this matrix, and let it be R1 up to RT and C1 up to CT respectively. And we will put the lengths of this, or we will denote lengths of these orbits on rows by capital omega I, and lengths of the orbits on the columns with omega I. If we take Mij to be the submatrix of the integer matrix M, that is consisting of the rows belonging to the row orbit Ri and the column belonging to column orbit Cj, we can denote capital gamma ij and gamma ij to be the sum of some row and some column of this submatrix, respectively. The sums of entries of any two rows or any two columns of this submatrix are equal, so the choice is arbitrary, and in this case and in this sense, capital gamma ij and gamma ij are well defined. So we can now define that matrices R and C, such that in matrix is T times T matrix, having the entries capital gamma ij, which are row sums, and C to be T times T matrix having gamma ij for entries, which are column sums, to be called row orbit matrix and column orbit matrix of the matrix M with respect to the permutation automorphism group G. And this idea of having orbit matrix of an integer matrix with respect to permutation automorphism group, we applied now to seidal and Laplacian matrices. It is not difficult to show that this lemma holds. So from now on, we will speak about seidal, Laplacian, and signless Laplacian matrices to be our integer matrices. So let G be a strongly regular graph with parameters v, k, lambda, mu. And we have seidal, Laplacian, and signless Laplacian matrices of this graph, respectively. And we can see that square matrices of seidal Laplacian and signless Laplacian have three different entries, depending whether on the position we have the same vertex, whether two vertices are adjacent, or whether they are not adjacent. So it is always this case that we have these three entries. So just to have more concise names, we will hereafter use M to be any of the matrices SL or signless Laplacian, which is corresponding to SRG. And I will speak about entries of M square matrix to be alpha, beta, and pi, depending whether we are speaking about seidal, Laplacian, or signless Laplacian matrix, because it is always depending on these three positions of the I and J. And matrix M is symmetric, so it means that M square is actually M times M transpose. Okay, so these facts about entries and about properties of having orbit matrix of an integer matrix, in this case, having an orbit matrix of seidal, Laplacian, and signless Laplacian matrix, were crucial for us to try to obtain the method that will give you conditions how one can use this matrix to obtain self-orthogonal codes. Okay, so in order to see what conditions should be satisfied to obtain self-orthogonal codes, we needed this crucial theorem to hold, which actually gives you the following. If you take G to be a permutation automorphism group of M, I remind you that M is now seidal, Laplacian, and signless Laplacian matrix. And if you denote with R1 up to RT and C1 up to CT to be the G orbits on the rows and columns of the matrix M respectively, And if you take capital omega I, capital gamma ij and gamma ij to be defined as I explained above, then you have this expression holds. So you have on the left side, you have the sum of this this statement to be equal to the something that is follows. That is, so if you take a look at this expression, you have that alpha, which I remind you is from this statement. Alpha, when you're speaking about seidal, is always v minus 1. If you're speaking about L, it's always like this, etc. It is multiplied with Kronecker symbol. Then you have beta with C, which is an element from orbit matrix, and this expression multiplied with pi. This proving this statement was crucial in order to obtain conditions for having the method of obtaining self-orthogonal codes. So how you can construct it? If you take G to be a permutation automorphism group of seidal Laplacian or signless Laplacian matrix, which are hidden behind M, which is acting with T orbits, and they are all of the same length, which we can denote by W. And if you take R to be the row orbit matrix of M with respect to G, and if P is a prime dividing alpha, beta, and pi, where alpha, beta, and pi are defined as above, then linear code spanned by this orbit matrix will, over the final field FQ, will give you self-orthogonal code of length T. Excellent. So if you have conditions that is arising just from the parameters of strongly regular graph, you can construct self-orthogonal codes. The sketch of the proof, this, as I said, this theorem and the whole method lies on the fact that we know what this expression looks like. You have all the lengths of the same, all the orbits of the same length, and you know what are the scalar product of your rows or orbit matrices, and if you have that P is a prime that is dividing alpha, beta, and pi, you will obtain self-orthogonal code. Okay, so this is the case when permutation automorphism groups acts with T orbits all of the same length. But this does not have to be the case. You can have also the case when G is a permutation automorphism group of a seidal Laplacian and signless Laplacian matrices. And this permutation automorphism group does not have to act in the way that it produces orbits of the same length. We can denote by omega j to be the lengths of the G orbits on the columns of M, and let W be an element from this length of orbits. Then again, you have a condition which gives you, which if it is satisfied, you will obtain self-orthogonal code. So if Q is a prime power, where P is a prime dividing alpha, beta, and pi, and if the lengths of the column have the property that P times omega j divides W if omega j is less than W, and if PW divides omega j if W is less than omega j, then the submatrix of orbit matrix, which is corresponding to S row orbits and column orbits of length W, will span a self-orthogonal code of length S over FQ. We used permutation automorphism group, we use the orbit matrices of permutation with respect to permutation automorphism group when this group acts in the orbits of the same length, but also when it produced the different lengths of the orbits. The third thing that we also show that can be used is something that we called fixed part of orbit matrix. What is it? The submatrix of an orbit matrix that is corresponding to the fixed rows and the fixed columns is called the fixed part of the row matrix R. And usually when you are taking the submatrix of orbit matrix that is corresponding to the orbits of rows and columns of lengths greater than 1 is called the non-fixed part. So if you take the theorems that I showed you before, it is very easy consequence that says if you have a permutation automorphism group of matrix M, and if you have corresponding orbit matrix, and if you have omega j to be the lengths of the G orbits on the columns of this matrix, and if you have that P is a prime that divides omega j, then if you take S rows that are belonging to the fixed part of orbit matrix, then they will span a self-orthogonal code of length S over the field FQ. So actually we used all, we can say, parts of orbit matrices of seidal Laplacian and sinuous Laplacian matrices in order to try to construct codes with nice properties. Okay, so these methods that I've showed you gives you methods for constructing self-orthogonal codes. Moreover, we were interested in seeing, okay, it is very nice to have a method that will produce you self-orthogonal codes, but we were also very enthusiastic in seeing whether these self-orthogonal codes would be more nice, that they can be as self-orthogonal in a way that maybe we can try to construct optimal ones, or if they are not, at least near optimal. So when I say an optimal linear code, I mean that we say that NK linear code is said to be an optimal linear NK code if the minimum weight of C achieves the theoretical upper bound, I mean here on singleton bound, on the minimum weight of NK linear codes, and we will call it near optimal if its minimum distance is at most 1 less than the largest possible value. And here when I'm speaking about optimal and near optimal, I'm referring to the Marcus Grassel table on this page, and it is called bounds on the minimum distance of linear codes and quantum codes. Okay, so we started to apply the method to seidal Laplacian and sideless Laplacian matrices of strongly regular graphs, and I will now show you what kind of results we obtained. So the method goes in a way that you have conditions which tells you that take parameters of strongly regular graphs, and you can see whether these parameters are suitable for use to obtain self-orthogonal codes. First, in this slide, we were using the whole seidal matrices to obtain self-orthogonal codes. It is possible. Why? Because a trivial automorphism group is actually producing you orbit matrix which is equal to the matrix as it is. So you can span a code with the whole seidal matrix, in this case, also with the whole Laplacian and signless Laplacian matrix, because these matrices are actually orbit matrices with respect to trivial automorphism groups. So we've taken in this table Peterson graph, all graphs with parameters 26, 10, 3, 4. It is known that there are 10 non-isomorphic, and all 4 non-isomorphic strongly regular graphs with these parameters. Their parameters are suitable for obtaining self-orthogonal codes, and in this table you can see what we obtained. So you can see the parameters of the codes, the parameters of the duals, and the sizes of the full automorphism groups. Those having the star are optimal and near optimal, and in this case we obtained optimal and some near optimal self-orthogonal codes. Okay, so moreover, we went on some other strongly regular graphs. And here we obtained codes, self-orthogonal codes from orbit matrices of seidal matrix of strongly regular graph with these parameters. We've taken a strongly regular graph with these parameters on which the finite simple group U34 acts transitively. You will see in these examples, I will always emphasize it acts transitively because I want to show you which kind of strongly regular graph we've taken. And these strongly regular graphs that we were working with have the big, huge full automorphism groups. They are nice. They were nice for us because we were searching for those with big automorphism groups, because then you have more potentially automorphism groups from which you can construct orbit matrices. It means more potentially nice self-orthogonal codes. And in these tables, you can see with respect to what, to which subgroup of the full automorphism group we constructed orbit matrices, the codes that we obtained, and the sizes of the full automorphism group. So this is from seidal matrices. And this is these are also codes obtained from orbit matrices of seidal matrices. Here we've taken the rank 3 graph with these parameters on which orthogonal group acts transitively. It has a huge automorphism group, and you can see that some of the codes that we obtain here are ternary codes that were satisfying the conditions, and some of them have huge automorphism groups. Even more, you will see even bigger automorphism groups. Okay, here it was Laplacian matrices that we've taken into consideration, and in this case, the strongly regular graph with parameters 1, 6, 5, 36 did not satisfy condition for obtaining self-orthogonal codes for Laplacian matrices, but its complement did. Since this is also strongly regular graph, we could take into consideration the complement. And here are the codes that we obtain. You can see how big automorphism groups of the codes are. This is also from Laplace matrices, but it is strongly regular graph on which Janko, on 280 vertices, on which Janko group J2 acts transitively. And here, for the first time, we obtain that conditions are satisfied also for obtaining binary self-orthogonal codes. Some of them are optimal, and some of them are near optimal. These results are obtained from signless Laplacian matrices, and here is very nice to show you how big automorphism groups of these codes are. As Dan said in his talk, if you remember, codes having the huge automorphism groups are suitable for more application, for example, for permutation decoding. And we saw that in our cases, the codes that are arising from this type of matrices actually have big automorphism groups. So potentially in the future, they could be good base for permutation decoding. Okay, so what can be done more with this method? If you take a little look on this expression, you can see that actually you can rewrite this expression and you can obtain similar expression, but with different factors, because you have alpha here, you have alpha minus pi. What does it mean? It means actually that you little bit change your divisibility property. You will actually obtain you could actually obtain self-orthogonal codes from strongly regular graphs that are not satisfying conditions given before. So you have even wider range of possibilities of using strongly regular graphs. And we have done that. It is not difficult to show that also for these divisibility properties, you can apply the same result, the same expression that we need for obtaining self-orthogonal codes. This different condition we applied on two very nice graphs, strongly regular graphs. One of them is Higmans-Sims graph. It is unique graph with parameters 122.06 on which the Higman-Sims group acts. And the another graph is Mclaughlin graph, which is unique graph with these parameters on which Mclaughlin group acts. And the codes here are the codes, self-orthogonal codes that we constructed. And the conditions that are satisfied for Higman-Sims graph are satisfying for seidal matrix, and for a Mclaughlin graph, Laplacian matrices are those that could be used for obtaining. In the case of also for Higman-Sims graph and Mclaughlin graph, we have that codes, self-orthogonal codes that could be constructed are those over F5. Okay, so what I told you in the beginning, actually we saw that our method is working not just over finite fields, but also over finite rings. So linear codes over finite rings are defined similarly as linear codes over finite fields, but here codes are modules, but here instead of vector spaces we have modules. And the most famous codes over rings are codes over Z4, which is the ring of integer modulo 4. This is something that I will just show you quickly because I don't have time now. But Z4 code is of length n is a Z4 submodule of Z4 to the n. And for Z4 codes, there are three ways that are defined: Hamming weight, Lie weight, and Euclidean weight, which are differently defined. And actually, they are depending on the number of the components of code word, which are equal to 1, 2, or 3. For Z4 code, they are actually the researchers that are working in this field are interested either in type 2 Z4 code or type 1. Self-dual Z4 code, which has the property that all Euclidean weights are divisible by 8, is called type 2. And if it is not type 2, it is called type 1. And type 2 Z4 code of length n, it is known that it exists if and only if n is congruent with 0 modulo 4. The minimum Euclidean weight of this type of code is bounded, and if with this expression, and if you have a type 2 Z4 code that is meeting this bound, it is called extremal. And what we were able to see, that our method for obtaining self-orthogonal linear codes from seidal and Laplacian matrices of strongly regular graphs actually works also for obtaining self-orthogonal Z4 codes from orbit matrices of this type of matrices. So we proved the analogs theorem, as I told you before, but in the rings of integers modulo n. It stays now to try to find nice examples and try to go deeper in this way of research. So I hope what was the idea is to show you how one can use matrices that are related to graphs in order to obtain nice results also in the coding theory. And with this, I would like to stop my talk, and I would like to thank you very much for your attention.
Thank you very much for this wonderful talk. Are there any questions to Andrea?
If I may.
Yeah, sure, please. Yeah.
So this is a list of successful experiments in a way, right?
Yes, because for example, for each graph that we've taken into consideration, we also obtained some trivials. So we didn't put them into account. And also for some groups, orbit matrices were too big, so we couldn't get the whole information about the code. The minimum distance was missing. Yeah, but
yeah. So I'm hoping there will be some theorems that will predict the outcome, you know, in a way where you say, if this is true for the strong irregular graph, this will be true for the codes or something.
Yeah.
The other thing that kept coming to my mind are the LDPC codes. You are aware of those, right?
Yeah, yes.
Is there a connection, or?
As far as I know, no, but this is definitely an interesting thing to try to see, because maybe there is some connection of using properties of strongly regular graphs. These matrices are huge, and as far as I know, for LDPC codes, you have to have sparse matrices.
Yes, that is correct.
So maybe they are potentially good to try, but we didn't.
Okay, yeah. Well, thank you very much for a nice talk.
Thank you.
Any further questions to Andrea? Well, if not, then let us thank Andrea again for this very interesting talk containing a lot of new information and new approaches. Thank you very much.
Thank you, Elena.
Yeah.